Hello. In this video, I'm going to give a few more characterizations of Pascal's triangle. Characterization 10. Imagine a pin at each location in the first n rows of Pascal's triangle. In other words, row 0 through n minus 1. Now there's a nice online applet that demonstrates this. Let me show you the concept. Here I am at my Pascal's Triangle websites page, and I'm going to use this applet right here, the ball dropping applet. And let me see if it'll work. In this example, we have 5 rows. Technically, it would be row 0, row 1, row 2, and row 3, and row 4. And let's release a ball and see what happens. Every time it hits a pin, it either goes left or right. Here comes the next ball and falls into that bin. So the whole idea of the binomial theorem, binomial coefficients, is it is an either-or situation. And this is typical. Oh, there was the rare one falling to the left because it had to turn left at every single pin. Now let me see if I can set this automatically. Yes, now I have this set up automatically and the balls are falling in. And you'll notice that the most common bins are the bins in the middle, because there's lots of ways for the ball to fall into the middle bins. We did finally get a couple to fall over here onto this right side. I'm going to see if I can pause this now. So this is kind of a probability experiment. How does this relate to Pascal's triangle? If we imagine a ball being dropped from the top, and each time it hits a pin, it goes left or right. The numbers in the row n are the number of different ways a ball being dropped from the top can get to that location. There's only one way a ball can get to the far left-hand position, and it has to turn left every single time. No right turns. To get into the second bin, in this case with row 7 going through 7 pins, we can go to the right one time. Let's 7 choose 1 because we're going to choose one of the times to turn right. Here's 7 choose 2 because we're going to go right 2 times and left the rest of the time, and so on. Here's another interesting problem. If you live here in this corner of this grid of streets and you're getting to Walmart and you want to find out how many ways you can go through the grid to get there, Pascal's triangle will answer that question. And now I'd like to show you a neat way to find any figurate number. Let's find the 6th pentagonal number. The pentagonal number can be subdivided up into some kind of categories here. The point down here is the genesis. This is kind of the zero-dimensional point. We have some sticks here, the radii, and then these triangular regions. We always have 1 as the first number for any polygonal number. Then we have the sticks. In this case, if it's a pentagon, we have 4 sticks. And if it's the 6th pentagonal number, they're going to be length 5. Then we have the triangular numbers, and these are 4 high. So we have 3 copies of the triangular number 4. 1 plus 20 plus 30 is 51. Now for the kth n-gonal number, we always have the number 1, which is kind of my bluish purple. Then we have our sticks. They're of length n minus 1. So we have k minus 1 times n minus 1. And then we have the green triangles, the k minus 2 triangular number times n minus 2. You might want to study this, pause the video and study this diagram. If you'd like to find more resources on Pascal's triangle, you can use this web page. Here's the URL. My name is Jim Olson. I hope you enjoyed these videos on Pascal's triangle and hope that you take time to learn more about this great triangle. Have a great day.